Yo, guys, what's up? Welcome back. Episode 131 today. 130, yeah. 130 yesterday. Yeah, we did Gyarados yesterday, so 131 today. I just want to make sure I uploaded the video yesterday. Low key. Okay, I did, yeah. So yeah, I uploaded 130 yesterday. So yeah, today's 131. We got a Lapras today, another classic Pokemon. OG Pokemon. Let's take a look at the sound, shall we? I don't know how I'm gonna do this sound. Alright, there you go. There's our sound. Let's take a look at the snakes and ladders problem here. Oh, man, so much riding, dude. Oh my gosh. Honestly, I have solved this question. I thought I solved it when I looked at it. I was like, I think I've done a snakes and ladders question. We did it recently too, April 13th. We did it. What's that? Like a month and a half ago. Let's take a look. I think we could do this. I'm not going to do this one today because this would be a very long problem. This would be probably about an hour-long problem. So we're going to look at some other stuff. Do you want to take a nap before my buddy comes? So we're going to try and do a couple problems maybe from Leetcode 75 and maybe do a graph problem. Kind of see where that takes us. We're really done with this Leetcode 75 though. We only got 12 problems left. Given two strings, text 1 and text 2, return the length. Let's get rid of that. We did do this recently too, May 5th. Take a look at this. Given two substrings, text 1 and text 2, return the length of their longest common subsequence. There is no common subsequence, return 0. A subsequence of a string is a new string generated from the original string with some characters can be non-deleted without changing the relative order of the remaining characters. For example, ACE is a subsequence of A, B, C, D, E. It is a length 3. So obviously we know this is like a DP backtracking problem, so my intuition here is that let's do Mimo is equal to this. Def backtrack. Right, we want to backtrack. What do we want our base case to be? Well, my goal is here is that we're going to have an I and a cur, right? We're going to add to our cur. Okay. We return an integer though. So I don't think it really matters. We can just get the length of that in constant time. So I think we add cur. So if we loop through this one, A, B, C, D, E, we go A, so either we can take or we can skip, right? So we take, okay, and then we check, well, we check is, will our current cur in text 2? If it is, then we update our longest string. Okay. So I guess if I is, let's do up here, let's take, if the length of text 1 is greater than or equal to the length of text 2, then let's do n is equal to the length of text 1. Otherwise, we can n is equal to the length of text 2, right? So this gets our length. Gets our length of longest longest sequence, okay? With our memo for later, right? And we check here, well, if I is greater than or equal to it's greater than or equal to n, then we would simply just return, right? Otherwise, we'd want to either, let's do take or skip, right? So either we can do, well, and check, well, if cur, okay, let's do if string cur in that's what I'm trying to think. In text 1 and string cur in text 2. That's definitely not right, bro. That's definitely not right. That's an interesting way to do it. If text I, so we start at I and j. That's the right way to do it. Try thinking it like that, but no, that's the better way to think about it, right? So if I is greater than or equal to the length of text 1, or I is greater than or equal to the length of text 2, then we want to return 0, right? Otherwise, if what's the key here for it? I guess if we're at the same spot, right? So if not Mimo DP, if DP IJ DPIJ, right? Otherwise, if text 1I is equal to text 2I, then we want to backtrack I plus 1 trying to think here. I plus 1, J plus 1. Backtrack I J plus 1. I think we're gonna need to do like a max here. A max. Let me do DP IJ is equal to backtrack And then I think we would just return dp ij return backtrack 0 0. Recursion depth exceeded. So are we not returning anything? The result dp ij is equal to result. We want to return our result. Want a max there? We is a max. I thought it was a max. It's a max, but we need to take the max of either one because you don't want to keep doing it if it's the wrong one. Max backtrack. This is meant to be J. Didn't do a J here. I don't have I here. There we go. There we go. I'm gonna come back to another problem. I'm just really sleepy right now, and I think I need to lie down for a bit. I did work out a lot this morning again, so I think I need to lie down for a bit. And then we'll continue doing a little bit more problems. If not, this will be a shorter video today, but I'll be back at it tomorrow. But I'll have another part after this either way, just to talk about it. So I'll be back. Gotta go to sleep. I'm extremely tired, so I'll be back soon. Yo, I'm back, guys. I'm back. I told you I'd be back. Oh man. Oh my god. I think it's like 4 hours later. Took a little nap. Went in the pool. It was pretty chill. But yeah, so we're gonna do a couple more problems. I'm feeling definitely a lot better. I was really tired that first problem, man. Like, literally about to fall asleep. I don't know what it is, man. But when I eat a lot of food, dude, I just like totally fall asleep, man. Like, so I'm feeling a little better. Let's jump into a couple more problems. Let's take a look at a tree again. It's been a while since we did a tree. I have to relook at what a tree is, dude. Given an array of products in a string search word, design a system that suggests at most 3 product names for products after each character of search word is typed. Lexicographically. I think, what does that mean again? Graphically of a dictionary. Okay. There are more than 3 products. Return a list of the suggested products after each character of search word is typed. So we give us a search word. They give us mouse. They want us to give products. I wonder if Leetcode has a video on this problem. He does. We're gonna take a look at this video. I'm not sure how to solve it at all.
You thought C++ was just C with classes? At least C-Lion can help.
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem search suggestion system. We're given an array of strings, products, and we're given a search word, and we sort of want to design a system that kind of simulates for the search word that we're given, in this case mouse. We're going to simulate typing one character from this word at a time, and then based on that new character, we want to suggest 3 strings from our product array such that the strings match the prefix that we have typed so far from our search word. Now that's a little complicated, so let's focus on an example. Our search word is mouse. We're going to type one character at a time. We're going to type the first character M. Now which one of these products have a prefix that matches what we've typed so far, which is just M? Well, all of these start with an M, but we're told in the problem that we want to suggest at most 3 products. So right now we have 5, but we want to do at most 3. Well, if there's too many, then we want to return the first 3 basically in alphabetical order. It would probably be helpful for us if this products array was sorted in ascending order. So I sorted the words in alphabetical order. We know that the time complexity of that is going to be n log n, so that's just something we're going to have to take. But so for the first prefix, which is just the first character, we want to return these 3, the first 3 words, since all of them are matching anyway. Now, next, we're going to add the second character, MO. So which one of these match the prefix MO? Well, still all 5 of them. So again, we're going to take these 3. Now, the result that we're going to be building is going to be a list of lists. So for M, we're going to have these 3 words. For MO, we're going to have the same 3 words. Now we're going to add the third character, MOU, and what we're going to notice is that only these last 2 words match. These 3 words don't match now. And also something you might notice is these 3 are never going to match now, because if they don't match the first 3 characters, of course they're not going to match the first 4 characters, because it's kind of a prerequisite to match the first 3 before you can match the first 4. Now that we've eliminated these from consideration, we won't ever have to look at them again. And I haven't talked a lot about how we're actually going to be implementing this algorithm, but this is definitely a helpful thing to keep in mind. And also notice how the matching words are close together in the array after we sorted it. That's not a coincidence. Of course, words that start with the same prefixes are going to be right next to each other in sorted order. That's kind of the definition of sorting based on alphabetical order. So for the first 4 characters, these 2 words are going to match. For the first 5 characters, again, these 2 words. You can see that in the output. So that's kind of what our output is going to look like. Now, all this talk about prefixes might lead you to a solution using prefix trees, aka tries. I call them prefix trees because usually they have to do with problems relating to prefixes, and it's a lot.
I have to relook at what a trie data structure is, man. Mm.
A lot more intuitive. Try is just a word. Prefix actually has some meaning to it. And that definitely will work. That is a way to get an efficient solution for this problem. But there's actually a slightly better way to do this problem, and I've kind of been hinting at that, and I'm going to show you. It's going to involve 2 pointers, and we're going to be able to solve this problem very efficiently. So to implement the solution, again, we are going to need to sort the words because we know that's going to be really helpful for us. And we know that when we eliminate some words and they don't have a matching prefix, we're never going to consider those words ever again. And we also know, due to the nature of alphabetical order, words that match a prefix are going to be close together. They have to be next to each other.
Got a billion-dollar web app idea? Now you can turn it into reality with Hostinger Horizons.
If this is in sorted order. Knowing that, we can use a 2-pointer method, a left pointer and a right pointer. Well, the way I've drawn these words, it's going to be kind of a top pointer and a bottom pointer, but in reality, this is going to be our left, this is going to be our right pointer. And what we're going to do is actually very simple. We're going to go character by character. So far, we get to the first character, M. Now, from this list of words, we want all words that have a matching prefix. So we're going to start at the top word and check, does it have a matching prefix, M? It does. So we can leave this left pointer here. We're going to do the same thing with the right pointer. It has a matching prefix. We're going to leave it right there. What this tells us is that this word is valid, this word is valid, and what that implies is that every word in between these is also going to be valid because they're in alphabetical order. If this one starts with an M, this one starts with an M, everything in between is also going to start with an M. It's not like it's going to start with a Z or something, because that would mean that these are not in alphabetical order. That would mean we didn't sort it, but we did sort it. Since all of these are valid, what are we going to do? Well, we want to return the first 3 in alphabetical order. So we're going to start. Start at our left pointer, count 1, count 2, count 3, throw these into a sub list, and then add that to our overall list. Now let's get to our second character, MO. Now we're going to just look at the second character because we already know that this word so far matched the prefix. We know this word so far matched the previous prefix. So now all we have to do is just compare the next character, O. O is equal, so this also matches. Same with this word, it also matches. So again, we just take the first 3, add it over here. Now this is where things get a bit interesting. We get our third character, U. So we're going to start at our left pointer. We're going to look at the third character. Is it a U character? It's not. So that means this word is not valid. So we eliminate this from consideration and we move our left pointer over here. And we're going to keep repeating this until we get to a valid word. The third character is an N. That's not a U. This is also not a valid word. It doesn't have a matching prefix. So next word, This also has an N in this spot. It's not a matching prefix. So now our left pointer is all the way down here. Third character does start with a U. So that's all we really needed to know.
My boyfriend and I have been arguing because he won't pay for YouTube Premium. But it's okay because I've just downloaded AdBlock from Capital.
So this does have a matching prefix. Now we go to our right pointer and check, does the word here have a matching prefix? U, again, U, so it does. So now we know that the words between our left and right pointers have a matching prefix. It's only these two words, but if there were words in between, we know that they would have a matching prefix as well. So now, again, we're gonna build our result starting at the left pointer. We're gonna count 1, 2, 3. Oh, there's not a third word. So in this case, we can only add 2 words because we went out of bounds. But we add the 2 words and then we continue. We're gonna, at this point, get to the 4th character. This has a matching prefix. This one does as well. So again, add these 2 words. And then lastly, the E. This has an E here. This also has an E. So these 2 words again for the last sublist, and that's pretty much the entire algorithm. I think what makes this problem hard is even though this solution that I just explained is actually pretty easy to implement and is very simple, this problem immediately, if you're familiar with tries or prefix trees, you're going to immediately jump into that solution, and that's what I did as well. But it turns out that there is a more simple and more efficient solution. So in terms of time complexity, let's say n is the size of the products list. We know that we did sorting, so we did n log n. We did our 2 pointers algorithm, which was big O of n. But in the worst case, we are going to have to iterate through every single word. So I guess you could call this n times, let's say, the length of every single word. And also, we know that we have to iterate through the input word as well. Let's say the length of that word is m. And then for each one, we might end up adding 3 words to the output. So technically we could say 3 times m, but that's just a constant. So we don't really care too much about it. Okay, so now let's code it up. The first thing I'm gonna do is declare our result so that I don't forget. It's gonna initially be an empty list. Second thing before we forget is to actually sort the input array because we know that it's unsorted when it's given to us. Then I'm going to initialize our 2 pointers. Left is going to be 0 at the beginning. Right is going to be the length of products minus 1, which is going to be the last index. And at this point, we're going to start iterating through every character in the search word. So let's get the length of the search word and have a pointer I going through it. Let's get the character at index I, which is going to be, let's call it C for now. And basically at this point, we want to start getting all the products that have a matching prefix. So to do that, we have to start eliminating the ones that don't have a matching prefix. Let's do a while loop for that. First, first condition for the while loop is just make sure our pointers are valid, because if our left pointer crosses our right pointer, then that pretty much means we have an empty list of valid products anyway, so we should just stop the loop at that point. But while that's not the case, and while, this is something we didn't talk about in the drawing explanation, but while the length of the product word at index left, because that's where we're at in our products list, we're at the left index. So this is a word. While the length of this word is less than or equal to I, basically we're checking, does it have an ith character? And second, I'm going to have an or condition here, which is going to check that the character for that word at product at index L, the character at index I is not equal to the character in our search word. So what this is saying, the product doesn't even have an ith character, or the ith character is not equal to the character that we're looking for. Basically, that means this word, this product, does not have a matching prefix. So what we're going to do is eliminate it from consideration. We're going to increment our left pointer. And we're going to keep doing that until either we've eliminated all words from consideration, or the word does have a matching prefix. And we're going to do the exact same thing starting from the right pointer. So this is going to stay the same. Product not at left, at right, and basically changing this to right as well. And then instead of incrementing our left pointer, we're going to decrement our right pointer. So at this point, we know that our range of products is valid. All products between the left and the right index at this point have a matching prefix. So what we're going to do for our result is first we're going to append to it an empty array. we're going to calculate the number of words that are valid right now. And we can get that by taking our right pointer minus our left pointer plus 1. This is basically the size of our window at this point, the number of words with a matching prefix. The reason we're doing this is because now we're going to start iterating through that list of words, the remaining words, and how many of them do we want? We want 3, but what if there aren't 3? Well, I'm going to take the minimum of 3 and the number that are remaining. Basically, if the number of remaining, let's say, are 10, then the minimum of 3 and 10 is going to be 3. We only want 3 words. But what if we only have 2 words remaining? Then the minimum of this is going to be 2. We're going to only have 2 words. That's exactly what we want, because if we only have 2 words, how can we possibly get 3? And I should actually probably use a different variable for this. I'm going to use j so that it doesn't conflict with this. And what I'm going to do now is result. We want the list that we just added right now to the end, so we can get that with -1 in Python. This is basically taking the last value in result, which is a list. So to that list that we just added, we want to append a word to it, and the word is going to be a product. And remember, from our products, we want to start at the left index and then, count 1, 2, 3 from there. So we're going to have the left index plus j, which is our counter in this case. And then that's pretty much it. After all of that is done, all we have to do is return our result and we should be good. But I'm noticing that I had a typo with products. It should have an S at the end of it, but I can see in a few spots I forgot to add that S. Sorry about that. But now let's run our code to make sure that it works. And as you can see on the left, yes, it does. And it's very efficient. So I really hope that this was helpful. If it was,
I do want to see the tree solution though. Add word. This is definitely a tough problem here, but we sort our products, right? create our left pointer. Left is equal to 0. Right, let's do left. Right is equal to the length of products minus 1. And we start by looping through each number in the search word, right? Make our char is equal to search word I. We get the character. We do while left is less than or equal to right, and the length of product I. Product I is less than or equal to I. Or product left I does not equal C. Left, right. I don't understand this here. I don't get this. I have to relook at this again.
Then that pretty much means we have an empty, not a list of valid products anyway, so we should just stop the loop at that point. But while that's not the case, and while this is something we didn't talk about in the drawing explanation, but while the length of the product word at index left, because that's where we're at in our products list, we're at the left index. So this is a word. While the length of this word,
I'm done spending an obscene amount of money on takeout every week. Done.
I'm getting back on track with Factor Fresh
is less than or equal to I. Basically, we're checking, does it have an ith character? And second, I'm going to have an or condition here, which is going to check that the character for that word at product at index L, the character at index I is not equal to the character in our search word. So what this is saying, the product doesn't even have an ith character, or the ith character is not equal to the character that we're looking for.
This is left. Does not equal char. The length of the product of right is less than or equal to I. Less than or equal to I, or the product of right I does not equal char. Then we want to append an empty list. We want to calculate the remainder. That's left plus 1. res -1. Append products left plus J. Then we want to return res. Res -1 dot append. So we're appending. I get why we're doing the -1 because we want to add with this one, but then we're appending products left plus J. Left being okay where we're at, so we got left here. Plus J would be the first one, then +1 would be the next one. I think that's why. Product. I think it's products. Right minus left. Oh, this is in the 4. Whoops. There we go. Interesting way to solve the problem. I was expecting to solve this using a tree. Oh, index is out of range. Okay.
It should have an S at the end of it, but I can see in a few spots I forgot to add that S. Sorry about that. But now
I don't know why this is not working. Ah, we have a plus here. It's meant to be a minus. We have to decrement. Oh man, my chest. There we go. Should get to the max. Yeah, nice problem. Let's take a look at our graph problem, and then we'll probably call it there for today. Oh, we already got a new one. Distribute candies among children too. We're gonna do that. We're gonna save that for tomorrow. Take a look at that tomorrow. Take a look at the graph theory today. Master binary search. No way. Man, they got something for everything, dude. Like. Keys and rooms. Man, how do these guys solve so many problems, dude? Like. Let's take a look at keys and rooms. I mean, we have solved it before. There are n rooms labeled from 0 to n-1, and all the rooms are locked except for room 0. Your goal is to visit all the rooms, however, you cannot enter a locked room without having its key. When you visit a room, you may find a set of distinct keys in it. Each key has a number on it, denoting which room it unlocks. You can take all of them with you to unlock the other rooms. Given an array of rooms, where rooms I is a set of keys that you can obtain. Visit room I return true if you can visit all the rooms, or false otherwise. Really? I mean, right, it's been a while since we saw this one. March, yeah. I think it's a pretty straightforward problem to think about. I think we'll create an adjacency list. Right, so if we're at room 0, we can get key 1, right? So really we can just make this an adjacency list where 0 connects to 1, connects to 2, connects to 3, and if we visit all the nodes, we keep a visited set. We can just check at the end if we visited all the nodes and run DFS from it. So to do that, let's create our adjacency list method, right? We pass in our edges, okay? We do, well, create a graph here. Then we go for edge in edges. We want to check, well, okay. Let's go actually for I in edges, graph I is equal to this. Make the nodes. Then we do for edge and edges. Shake it to the max. Let's change this for source and edges, for dest in edges. Let's do graph source dot append dest. Return our graph. We do graph is equal to adjacency list, and we pass in our rooms. Let's print our graph. I don't know why this is not working. For I in edges, graph I is equal to just an empty list. We need a dictionary. What is wrong with this? Using a list. List indices must be integers or slices, not a list. Ah, man. Shit, that's so bad. Length, edges, colon. Graph I is equal to rooms I. There we go. 0, 1, 1, 2, 2, 3, 3, nothing. Okay. Then we can run DFS here. DFS. We want to pass in our source. I think you can probably do this without DFS, to be honest. But I don't know. I think we're going to do it anyway. We do our node. Who's an array? Probably just passing our graph too. I guess we can just kind of start from DFS 0, right? We do DFS 0, pass in our visited. Let's create a visited set. So we pass in our visited, and we pass in our graph. Okay. We go here and we do, okay, well. We visited dot add node. We loop through for I for neighbor in graph node. Okay, gonna append that neighbor. Neighbor dot is it dot append or is it dot what? DFS, passing our neighbor, passing our visited, and our graph. Do we need a base case? I feel like we always need a base case. Do we need a base case? I feel like this is pretty straightforward. We're just doing visited.add. I guess our base case would be, well, for node and visited, we would just return. We don't want cycles, so I guess we could just remove this, actually. Yes, then we would just return, well, return the length of visited is equal to the length of rooms. I think that should be right. There we go. Probably didn't even need an adjacency list. Probably just could have. I think adjacency list was a waste of time, but yeah. Alright, well, I appreciate you guys watching. We're going to call it there for today. Yeah, I'll see you guys tomorrow for a little Sunday session. See you guys later.